continue. Okay, so in the last class we actually have done recurrence relation, that was completed, and we have seen that there are actually six recurrence relation that you should know, out of which the first four one you have to derive, and the other ones, other two, the last two in fact is a part of those four. Okay, you can just do some adjustments and do it. So in a similar way, we are going to do numerical problems, but the catch here is that when you do your numerical problem, you are expected that you know the Bessel function and its results. That means the recurrence relation, and then only you can proceed with the numerical. So we are going to just look into one or two problems, and you will see that it will probably take some time to solve it initially, but then you'll get the hang of it. Okay, because if you remember Bessel function, you can easily solve it. So this is a set of three numericals all comes together, and I'm giving it to you together. Okay, you'll find this is actually a very common problem. um, so let's just try solving it. Okay, so this is your first one. So that means j of half of x. So we have seen that Bessel function is in the form of j and x. I'm not talking about the differential equation, I'm talking about j and x here, which is actually the Bessel function. Okay, so this is one problem. So with the same set, if I just in place of m I can take minus half of x, this would be again root over of 2 by pi x cos x. I'd like to suggest you that for now maybe it's not needed you remember these results, but for your exams and all entrance exams where there may be multiple choice question, even if you remember these results, it can save a lot of time because you will know your answers directly. Okay, so that may be helpful, but right now you don't really need to worry much about remembering this. It's a simple thing. So if I take this should be 2 by pi x. So I don't think it's very difficult to understand the third one. If the first one is a sine term, the second one is a cos term, you take the square and add them up, sine and cos will get cancelled out. You just got 2 by pi x. Okay, that's it. So let's just try proving the first one. Okay, and the other ones will follow easily. Okay, so you can just prove one, the next one is easy. So j and x. So that means that obviously I have to remember what is Bessel function. Here at this moment I am not using the recurrence relation, so I just need to start with the Bessel function. Starting step is very important to remember whatever results we have actually derived, divided by factorial r gamma n plus r plus 1. We have got 3-4 more series that we need to study, and x by 2 n plus 2r. Okay, so that's your Bessel function, and what it means is I can make it a series because there is a summation there. I can make it a series. Now you'll ask me that how we're supposed to make it, why we should expand this. The reason is we have got a sine on this side and the sine series, so that means you have to expand it in such a way that finally you are going to get a sine series, and that's the reason. Okay, so as soon as you look into it, this should strike. And for this what we're going to do is initially r is equal to 0, so minus 1 to the power 0 is 1, factorial 0 is 1, so this would be nothing but divided by n plus 1, and this is x by 2 n plus 2 into 0 is 0, so that's x n by 2n. So I'll just write it down as x to the power n divided by 2 to the power n. I'm expanding this, that means I'm putting r is equal to 0, 1, 2 and so on. Let's take one more term. Let's take r is equal to 1. If I put 1, it will be a minus here because of this. So let me just put a minus term. Okay, and then I can again write it down as 1 divided by, this is factorial 1, so that's just 1. Okay, and then n plus 1 plus 1, so it is gamma n plus 2, and then I have got x to the power n plus 2 divided by 2 to the power n plus 2. And then I can take a plus sign and then 1, it's square, so it is positive, so it will be alternate plus and minus, which is something which I need. This is factorial 2, so I can just write it down as 2, and then this would be gamma of n plus 3. So this is going to increase like this, and then we have got x to the power n plus 4 divided by 2 to the power n plus 4. So we have this, and then minus, and then it will keep on continuing. Let's try solving it further. What I can do here is, I can actually take up 1 divided by gamma n plus 1 as common, and x to the power n by 2 to the power n also common. I can take everything common here. The first term I've taken the entire part, so it will be 1 minus 1. Now if you remember, I did tell you, if you have something like gamma of n plus 2, you can write it down as n plus 1, 1 less than whatever inside gamma, and then gamma n plus 1. So that means I can expand this n plus 1 into gamma n plus 1. Gamma n plus 1 is already taken out, so that means I have just got n plus 1. Yeah, x to the power n, 2 to the power n, I have taken it out, so I'm left out with x to the power 4 divided by 2 square, so that's again 4. Okay, done. Next, let's just do the next term. 1 divided by 2, this is n plus 3, so that means it can be written as gamma of n plus 3 can be written as n plus 2, n plus 1, gamma n plus 1. Expand this using the same logic, you're going to get this. So that means I can write it down as n plus 1, n plus 2, and this would be x to the power 4 divided by 2 to the power 4. Okay, so that means 16, so I'll just write it down as 4 into 4.
So that
Let's
is
say
so that is x to the power 2, first one. Sorry, second term, right?
2 1, oh sorry, yeah, x square, that's true, x square. So when I'll make the final series, I'll realize that okay, I made that mistake, so obviously very important. Yeah, so now the aim is, actually I'm going to find out what is j half. That means in place of n I have to put half, so put n is equal to half, right? So in that way you actually get your value of jnx, okay, and then this n will be actually replaced by half. So what I can do here is I can just simply write it down as 1 divided by, this is half plus 1, so this would be gamma of 3 by 2 into x to the power half divided by 2 to the power half. If we take this would be 1 minus 1 divided by half plus 1, so that is 3 by 2 into 4. We're just replacing n with half, okay, so I'm doing it directly. You also should do it directly only, don't use another step, okay, it will take so much time. Plus 1 divided by 2 times half plus 1, that is 3 by 2, half plus 2, that is 5 by 2, then we have got 4 into 4 into x to the power 4, and so on. Simplify this, get cancelled, it's 3 2, done. This and this gets cancelled, and then this gets cancelled, this is there. So we are getting a term which is actually something which we call as factorial. So if we just have a look here, and I hope you know this, this is 1 by gamma 3 by 2, so that means I can write it down as half
1 by 2
gamma
gamma
half.
by 2.
Yes, correct, you know it. Then what is gamma half? Anyone
The root
remembers, which
over
is
pi, I think.
root over pi? Absolutely correct, root over pi. Okay, so this is gamma 3 by 2. So I have to remember this, and that way I can do it in this way. So this is half root pi, so that 2 can be taken up, divided by, I can have it as root pi, and this would be root over of x divided by 2. This is nothing but 1 minus, this is 2 3, so I can write it down as x squared divided by factorial 2, and then I can take it to be plus, this is 2 3 4 5, so that's factorial 5, right? Not 5, sorry, I think I made a mistake here somewhere. 2 3 4
Yes, sir,
5,
that
yeah,
is factorial 5.
that is factorial 5. But then we cannot have, okay, sorry, this is factorial 3 now, not 2, right? This is
3,
factorial 3,
yes, sir.
yeah, correct. So this would be x to the power 4 divided by factorial 5. So if expand the sine series, this is what is the term. The sine series, this is our sine series. Okay, let me just be uniform with my notation. Okay, factorial 5 and then minus and so on. So if you look here, this is 2 at the bottom, there is 1, so it will be 1 minus half, so that root 2 will go on top. Okay, so this and this is pi x. Okay, this is some mistake is there, it seems. X to the power n, right? Yeah, oh sorry, yeah. If you look into the original term, it is x. Okay, and this is still not the sine term we have. Okay, it is not still the
So we
sine
have
term.
to take
So
1 by
yes,
x out.
correct. So we can take it like root over of 2 by pi, it's there, and then there is a root x here, and then what we can do is we can multiply it with x and divide it with x. Okay, and now what we do is, if we divide throughout by x and take one x inside, okay, I will just do it here only. Okay, let me not go to the next page. I will take one x inside. I'm not doing anything here. Okay, we are just taking one x inside because this is still not the sine series. Okay, if I take one x inside, this would be x minus x cubed by 3 factorial plus x to the power 5 divided by 5 factorial minus and so on. This is the sine series. Okay, this is the sine series, so please don't get confused here. I think lack of space cramping here, but then it's easy. Root over of, this is 2 and this is root x divided by x, so x minus half, the root x will go at the denominator, so this is 2 divided by pi x, and this is now the sine series, so this is sine of x. So this is how you basically prove it. So the thing here is that you have to remember what is sine series, and you have to adjust everything in such a way so that you are getting in series, right? Similarly, you can do it for cos. So what I like is all of you just try for cos. Up to this, it's the same, right? Up to this step, it's the same. So you can write down this and then replace not with half but with minus half, and convert this in such a way so that you are actually getting a cos series. So that will be x to the power 4 divided by factorial 4x square by factorial 2 and so on. Okay, so all the even terms will be there. Okay, so let me give you maybe 2 3 minutes, 5 minutes max. It should not take more than that. Okay, and then you should be able to get the cos series. Just check for cos series once, and then we will go to the next sum. So cos series, I don't think I need to solve. You can just check it. Okay, but tell me if you're getting it. You have to get it now only. Check. Okay, so when you put n is equal to minus half, you should get the cos series. So anyone can tell me how much you're getting? You're getting the cos series. That's more important. So this is 1 divided by gamma n plus 1. So that's minus half plus 1. So that's gamma half. Straight away you're getting your pi value. And this is x to the power half. So it's minus half.
Yes, sir, I got.
You got it right. Okay, very good. Others should also get it. Should not be very difficult. Right. Just put minus half. That's it. You get 1
Yes, I got it.
minus. Got it? Very good. So it will be x to the power 4. 4 minus half. So this is half plus 1 divided by 2 into half, then 3 by 2 into 4 x to the power 4 and so on. So it's all about getting that series correctly. That's it, right? So I get 2 here. Okay. Here also, you don't need to worry much about this. This is 2 is on top, it will minus half, and this is it will come at the bottom. So this is relatively easier. So 2 divided by pi x. Don't really need to work on anything here. It becomes automatically 1 minus, okay, this is x square. So it is 1 minus of x square by factorial 2 plus x to the power 4 divided by factorial 4. Okay, this cancels 4, so 432 factorial 4 and then so on, right? So this is a cos series. So this is root over 2 by pi x into cos of x. Okay, the third one I'm not doing it because simple way, the square and add both this and then you should get this. Okay, let's take some more sum. Okay,
Sir, please third
uh,
one question.
yeah, third one, you got the third one right?
Yes,
Third one
sir,
is
that question. I have not
okay, okay,
written that.
okay.
One second.
So all of you please write down the third question. Solving, I don't think I need to teach you. It's very easy. Just take the first two results, square and add. That's it.
Yes, sir.
Okay, good. So let's go for a new sum. Okay, let's take one more example. There are so many sums to solve using this. Okay, so you have to just take care that you do it correctly. Probably one of your assignment question will be from here. Okay, prove that ddx of x j n x j n plus 1x is equal to x j n square minus j n plus 1 square. So you have to prove this. Okay, so what we do is we'll obviously start from the LHS and we see that there is something which is we are differentiating. Okay, so let's try doing something here. Okay, so LHS is ddx of, you do it, I'll also do it, let's see. Okay, it should not be very difficult, it's all mechanical. Follow the steps and procedure correctly and you should get the result. Okay, so it's basically a function of 3, 1 2 3. So you have to use this differentiation rule. So let's say I have differentiated x and I've kept the other two constant. So ddx of x is 1. So this is jnx jn plus 1 of x. Then I'll take a plus. I'll keep the other two constant. So maybe I can keep x and jn plus 1 constant. The second term I'll differentiate. So I'll get jn dash x. So there are recurrence relation of jn dash also. So we're going to use those. And then finally the third term, that is jnx, will x and jnx will remain outside and I will differentiate n plus 1. So jn plus 1 dash x, done. Okay, so once this is done, okay, I can combine certain things. So I won't write down this x again and again. I'll just write down in this way, jn and then jn plus 1. You can also do this in exam, okay, it doesn't matter, you don't need to write down this x again and again. If you just write down jn, it's understandable, at least for these steps. Jn plus 1 plus, I can take jn, and I will take x, jn plus 1 dash together. Now let's just get back to the recurrence relation. So now you will understand that why we need to remember the recurrence relation, or why are we even deriving it at the first place. Else you have to do such a long sum. Okay. One of the relations that we have actually checked when we were actually doing our recurrence relation is njn minus x j
Jn plus
n
1.
plus 1, right? And then we also had this relation x j dash is equal to minus n j n plus x j n minus 1. Okay, so if we just want to find out what is jn plus 1, okay, so what we can do is we can write it down as this x j dash n plus 1 is equal to, I can take a minus in place of n, I can write it out as n plus 1, and then this would be jn plus 1 plus x. In place of n, I will write down n plus 1, so plus 1 minus 1 will get cancelled. This would be x j n. Okay, so I can write it in this way, and that way I can actually replace it. So here you have got the RHS, okay, in this relation. So I will keep on, okay, let me write it down LHS only. I've expanded it, we're just expanding this. I'm just going to replace the values now, okay. So in place of jn, it will remain as jn plus 1, it will remain, the first term doesn't change, plus xjn dash, xjn dash. So this xjn dash can be written as njn minus x jn plus 1 plus 1, and then we already have a jn plus 1 outside, plus this is jn, we have got xjn plus 1 dash, so this would be minus of n plus 1 jn plus 1 plus x jn, right? So obviously we are going to just expand this, so jn plus 1. So do it very carefully, okay. You can see that even I am also making mistakes sometimes, so you have to be very careful. N jn plus 1 minus x jn plus 1 square 2 times, plus this is minus, I'll try to expand this together, okay, so that we don't have to write down one more additional steps. Let's just do it. So this is a minus n there, so I'll just write it down as minus n jn plus 1, then this minus is still there, okay, so this is minus 1, so I'll take it minus jn plus 1, and then this is jn will jn square, so it will be plus x of jn square, okay. So I think we've got the result here very easily. It was just about remembering a recurrence relation, that's it. So this gets cancelled with this gets cancelled with this, we are left out with this too, okay. So that means I can take out x, and within the bracket it would be jn square minus j plus 1 square, okay, that's the answer. So proved. So it's not very difficult. What I feel is, when I was doing my masters, Remembering these results is very important. One plus and minus, I make a mistake there. I tend to falter and give wrong answers. Very important to remember that way. Okay, let's take a sum here. Okay, one more. So this one is something which I'm giving it to you. You try it for some time, and if you're not able to do it, maybe I will solve it. Okay, let me take this example. So the question is, prove that, okay, d dx of what, jn x square plus jn plus 1, okay, whole square x is equal to 2 times, to show this, n divided by x jn square x minus n plus 1 divided by x jn plus 1 square x. You have to prove this. Okay, so think about it, think on the left hand side and try doing it. Okay, please remember, jn square x does not mean 2jn dash x. You are squaring the uh, function, Bessel function. You are not writing ddx of x square. So remember this, jn square x can be written as jnx into jnx. So differentiate one, keep the other one constant, differentiate the other, keep the other one constant. So it will be 2 times jn dash. Try doing this. If you differentiate this, if you take, that's the starting hint, if you differentiate this, jn square x, this would be 2 times jn dash. Just dropping the x there, convenience. Okay, let's try doing this, and then 10 minutes maybe logical, so should not be very complicated. So just take this x jn dash. So since jn dash, so obviously a jn dash we have to take, and we have taken it with x, so it is n jn minus x jn plus 1. So we've done it this way, but I don't need x jn dash, I need only jn dash. So that means this jn dash is equal to n divided by x, divide throughout by x jn minus x by x is 1, so it is j of n plus 1. This is 1, and we do have the other relation. Let's use that also. So in the previous problem, in this problem, both times we are using the same recurrence relation result, n jn plus x jn plus 1. It's also a result we have. I need jn plus 1, so I'll just take jn plus 1 dash is equal to minus of n plus 1 divided by x into j of n plus 1 plus jn. So what you can do is you can replace this jn dash and jn plus 1 dash. Okay, and when you replace it here, okay, here you should be getting this. So I'm not going to do it. Okay, if you just replace it, that's it. It's only about adjustments. That's that. We give you one more problem, okay, and then we will stop. Just okay. So this question is integration x cubed j naught. I'm not writing x here. It's obviously a function of x. Dx is equal to x cubed j1x minus 2 times x squared j2x plus c. That means you have to just integrate it. Okay, so we'll take one more recurrence relation. we have, okay, by, so the relation is d dx. This was there in intermediate step also, we got somewhere. X to the power n jn is equal to x to the power n and then j of n minus 1. This is a relation that we got, okay. We need j0, we need j1 and j2, j0 in terms of j1 and j2. So j0, it means that if I put n is equal to 1 here, 1 minus 1 will come 0 and I'll get j0 there, okay. So it's obvious. So once I know the recurrence relation, the other steps is not difficult. Just understand and do it. So if you do it that way, I can simply write it down as d dx of x j1 is equal to x to the power 0, x to the power 1, sorry, into j1 minus 1 is 0. So this is the result that we have. Let's mark this as number 1, and we can continue this and put n is equal to 2. I'll tell you why we're using it, okay, why to get it that way. So if I put n is equal to 2, I can just simply write it down as d dx of x square j2 is equal to x square 2 minus 1 is 1, so it is j1. So that's equation 2, okay. So if I just integrate this, here, integrate this with respect to dx, this dx and that dx will get cancelled with d of x squared j2. So we can also use the reverse idea that differentiations complementary is integration. So x square j2 is equal to integration of x square j1 dx, right? You can also do it this way. Now what I need, we have got an x square here and this is a j2, so we already have this term, but on this side it is actually x cubed, okay. So we will do certain changes here, okay, and let's see what happens. This particular first term we need x cubed on this side and then we need to integrate. So what we can do is we can multiply it with x cubed, x square, right, because there is already one x, okay, and then integrate it. So maybe I can write it down here, multiplying equation 1 by x square and integrating. So if you do it with respect to x, obviously we have got it as x cubed j naught into dx is equal to what we have on this side is this. So this side also obviously we have to integrate both sides, and this side we don't have, x square we have to multiply. So I will take x square and then I will take d dx of x j1 dx is equal to, okay, that's equal to it, done already. Check this x square I've taken and integrated it with respect to x, okay. Now what I do is I will do it by parts, so maybe I can just expand this. So I will do it by parts, integration by parts. So first term, let's take x square, which is constant, and the second one is I have to integrate this, right? So if I integrate this, dx will get cancelled, I'll get d of x1j, right? So that means this will just remain as x1j, okay. I hope you know these things. Integrate d dx of, let's say, a term a with respect to dx. You can always cancel this out, d of a. That means it is simply integration of d of a. So that's a, right? So that is what we are doing here. This thing. So the first function. In the second function, we have to write down, let's say, a minus, and then we will integrate, keep the integration sign, d dx of x square now. So d dx of x square is 2x, okay, and then we can just have that x1 xj1. So then I'll get integration of that, remember, by parts dx. So we have it. So that way this one would be nothing but x cubed j1 minus, this is 2 times, can come out j1, okay, can come out, okay. So we have got 2 times x square, so this would be 2 times of x square j1, okay, plus c is obviously there because we have already integrated it, okay. Now this is x square j1, you can see here, okay. Okay, I think I've written the recurrence relation, I mean the proof here wrongly. Let me just check it here. Yeah, yeah. This is not 1. I think this is integration of, yeah, this one you can see. So you see integration of x square j1 dx. So integration of x square 2 can be taken outside. This is integration of x square j1 dx, and integration of x1 j square j1 dx is x2 x square j2. So this will be x square j2. So you see these steps we sometimes miss. Okay, it becomes a bit confusing. That's the proof. Proved. That's the reason I've taken this. But this you can do it later also. Okay. Sometimes we see that maybe this is a typo. It should be j1, but no, it's not true. Okay. You are integrating x square j1 dx. Okay. So if you use this recurrence relation and check for 2, we'll see that integration of x square j1 dx is equal to x square, one more added here, so j2. So that's why I have replaced it with j2.